Hello, welcome back to CS560 algorithms and their analysis. Okay, so today we're gonna carry on with our topic of dynamic programming. So last time in the last video, we introduced the top-down and the bottom-up approaches for solving the rod cutting problem with dynamic programming algorithms. And we analyzed the code, and we also analyzed the running time of both methods. So basically, it's quite straightforward to see that the bottom-up method has a quadratic running time because it's two nested for loops that results in a arithmetic series of total executions needed. And it turns out that the top-down method, the memorized cut rod, also has the same running time. Okay, so here we'll introduce another technique of visualizing or analyzing the running time for the algorithms for the dynamic programming solutions. So it's something called a subproblem graph. Okay, so it looks like it's basically a based on the recursion trees, but with the same nodes, or the nodes with the same values merged. Okay, so it looks like a status machine. So it's like the transition between stat 4 to stat 3 to 2, 1, 0. Okay, so here this graph is particularly for the rod cutting problem, and here the 4, the node with the 4 in it, it refers to the solution for R4, which is the maximum avenue of cutting the rod of length 4. So in order to solve R4, we need to depend on R3 and R2, R1 and R0. So the arrows from 4 to 2, from 4 to 3 to 2 to 1 and to 0 indicates the dependencies. Okay? And we have similar dependency from R3 to R2, 1 and 0, and R2 to 1, 0, and R1 also depends on R0. Okay, so this arrow or directional, the edges with directions describes one thing, that we need to solve the smallest subproblem 0 first. Only after that can 1 be solved, and only after 0 and 1 are all solved can 2 be solved, etc. Okay, so and there's only one occurrence, one appearance, or one instance for each for the node of distinct value. So the node 0 only appears once, and so for all the other distinct nodes. So that means we didn't solve 0 more than twice. Okay, more than once. We just solve it once and for all, and later on we can use the existing solution without doing any extra computation. So it's more clear if you compare the subproblem graph with the recursion trees. Okay, so on the left it's the recursion tree of the naive cut rod implementation, which is a recursive algorithm, and you can see that if it's this very inefficient algorithm, the recursion tree is basically very large, right? Very bushy, a lot of branches, and to solve the problem of size 4, you need to have 3, 2, 1, 0 solved. Okay, But in order to solve 3, because this is a recursive algorithm, it will need to solve 2, 1, 0 again, which is already solved here. So that's caused inefficiency. And from the graph, you can see that there are a lot of repeated nodes. 2 is here and here, right? And 1 appears here, 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 here. All the nodes, a lot of nodes appear multiple times. Okay, so somehow if you could merge all the duplicates, all the repeated nodes in the graph on the left, you will get the graph on the right, which is the subproblem graph generated by a dynamic programming approach. Okay, so if you merge the 2 nodes together, the two nodes, and you merge the 1, 2, 3, 4 1 nodes and all the zeros together, it will show you something like this. Okay. All right. And if we turn to the Fibonacci problem, we can use the same technique, the same subproblem graph to describe why the dynamic programming approach to Fibonacci is also efficient, because you see, in order to compute the Fib3, the third or the fourth Fibonacci number, you need to compute. It depends on the Fib2 and Fib1. Okay, and later on, when you compute Fib4, you also need to compute 3 and 2. Okay, but you will reuse the previous results, and you don't need to drop new branches from 4 to 2. Okay, so this connection from 4 to 2 is the old node that is already referred to by the node 3. Okay, and so on. So this is the subproblem relation or subproblem dependency in a Fibonacci problem. Okay, so that's it for another technique of analyzing the DP algorithm. Okay, so next we're going to introduce some supplementary materials that may be helpful to better solve or better understand or to gain more fine-grained solutions out of the for the rod cutting problem. So far we have solved them with 2 methods, top-down and bottom-up, and the two procedures that we implement, they both return the optimal solution, which is the maximum revenues for an input of certain length, right? But that seems not sufficient, because it's a task that we want to know how each step we want to do, right? We want to know where is our first cut and where is our second cut, and where are all the places that we need to do the cuts, right? So that's a very particular need for these questions. So we can do some simple modifications to the existing algorithms so that they can not only return the maximum revenue, but also the ways of cuts to obtain the maximum revenue. Okay, we can make the change simply by remembering or recording not just the optimal value for each subproblem, but also the choice that led to the optimal value, optimal solution. Okay, so one way to extend or to modify the bottom-up method, bottom-up approach, is that look at the line 8. Okay, so we have one more line of code. So the difference between this extended version versus the original bottom-up version is only the line 8. Okay, so we added a new algorithm, a new array of length n, and they all new. They are the S array is also initialized first. Okay, so that's the additional resource we need. Okay, so what we do at line 8 is that after we spot a new candidate for Q, right, which is after we have computed a new candidate for Q, which is the currents, which is the price of length I plus the optimal cutting results on the remainder on the subproblem, which is of length j minus I. So that means in order to obtain the Q, we need to cut the position at I, right, for the subproblem of size j. Okay, so we will record this position into array S. Okay, because it is a way to get a better revenue. Okay, and afterwards, after all the rest of the code are executed, we will return array R and S at the same time. Okay, so if we look at this any simple example here, if we call the rod cut problem, call the modified version on the input of length 10, it should give us not just the R array, but also the S array. So the R records the maximum revenue for all input lengths, and the SI remembers the place where to place the first cut. Okay, so for example, in this S of 9, which is the value 3, it basically means that in order to get the optimal value from a rod of size 9, the first cut should be of size 3. Okay, so we need to first cut a rod of length 3. Okay, and what about the remainder? The length of the remainder is 9 minus 3, which is 6, right? And then we refer to the table again to see what S6 is. Okay, and it tells us that S6 is 6, which means that we will keep the remainder of length 6 as a whole, right? The first cut is at length 6, so that basically means not cutting it. Okay? So similar example, another example, if you look at the input length of 10 and the SI means 10, so that means for input rod of length 10, you cut at a position of 10, which is equivalent to not cutting it, right? Because it gives us the best price of not cutting it. Okay, so based on this extended version of the bottom-up rod cut problem, we can bottom-up cut rod algorithm. We can use this helper procedure to output the sequence or the order of cuts that we need to make, right? So given an input size of n, we first obtain the optimal solutions in R and optimal ways to cut in S, and then we will print all the elements in S in such an order, right? Each time we compute S of n, we will minus it from n, because we want to compute the remainder of the length. Okay. So in this example, if the input is of length 9, then we first print S 9, and then we print S6, which gives us the order of the cuts. Okay? So this is just a simple and nice way of how to improve the bottom-up cut rod algorithm to make it more useful, to provide more information. Okay, so now let's do a little recap of everything so far we have covered about dynamic programming. Okay? So there are two major indicators of when we should use dynamic programming. Okay, we have we first introduced the Fibonacci example, and then the cut rod problem as the second example. So they all share such properties. So first of all, the problem needs to show something called optimal structure. Okay, so the definition is provided in the slide and in the textbook, and it's basically saying that the problem should the optimal solution to the problem should contain the optimal solutions to the subproblems. Okay? And it's similar to the requirements of running divide and conquer algorithms. Okay, but this is not a sufficient condition, because when a problem exceeds such a property, we might use dynamic programming, but it's also possible that we can use other different approaches like divide and conquer, or as the greedy algorithm that we're gonna talk about in the coming lectures. Okay. So a second indicator of using dynamic programming is this is really important part actually. So it is the overlapping between subproblems. Okay. So when the subproblems are unique ones or distinct ones that are totally different from each other, then the dynamic programming didn't help at all, because it doesn't matter if we remember the solutions to this one subproblem or not. Okay? We can use recursive algorithms like divide and conquer algorithms to solve the problems. Okay? But if the same subproblems appears again and again repeatedly, then that's really a good sign that we should consider using memoized way or bottom-up way to solve the algorithm. And remember, after each time we solve a subproblem, we need to remember it. Okay. So in contrast, like in the case of divide and conquer, the subproblems, they are all different. So each time we divide a problem, it will result in two brand new subproblems, and those subproblems are not likely to appear, not likely to duplicate. Okay, so that's it for the first part of, or actually the second part of rod cutting, the second example of rod cutting of dynamic programming approach. And next we're gonna talk about a third example, which is matrix chain multiplication problem. And this is also a very typical and successful usage of dynamic programming. And we will have one homework assignment question that's about this matrix chain multiplication problem. So I guess after this lecture, you are able to do the problem to the question on the assignment 2. Okay, so this problem is defined like this. So the task is to, given a sequence or a chain of multiple matrices, let's say n matrices. We want to multiply them together and then have a concrete result or a resulting matrix. That is the result of doing this sequence of matrix multiplication. So to be clarified, it's different. It's a different problem with the matrix multiplication problem that we talked before. We talked before in a divide and conquer lecture, right? We said that in order to multiply two matrices together, there's a way to improve the efficiency of it, of using some divide and conquer tricks. We talk about Strasson's algorithm, right? And that algorithm is an optimization based on the multiplication between two matrices. Okay, and now the problem we are talking about here is a matrix chain multiplication problem. It's not the multiplication between two, but a chain, a whole lot more, and this chain could be very long. Okay, so we wish to compute the products. We can represent this product by writing the matrices together. Like A1 is a matrix, and then we write A1 next to A2 and blah 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 until AN. We write this bunch of matrices together in order as a way to represent the final result, the final product. Okay, so this is a interesting problem because matrix multiplication is associative. So that means you can put parentheses, you can put basically any number of parentheses into the product position, into different places, but it will yield the same product. Say in this example, if we have 4 matrices from A1 to A4 that we want to compute the multiplication between them, we want to, maybe we can multiply A3 and A4 like the first row indicates. We can multiply A3 and A4 first, and then we multiply A2 with the result of A3 times A4. Okay, and finally we compute A1 times the result of A2 times A3, A4. Okay, so you see the parentheses define the order of the multiplication computation. So in the second example, in second row, it's a different order. We compute A2 times A3 first, and then times that result with A4, and then times the result with A1. Okay? Or we can, like row 3 did, we do A1, A2, and then A3 and A4, and then multiply their results together. Okay? So we say that a product of matrices is fully parenthesized. So if either it is a single matrix or the product of two fully parenthesis matrix products. Okay, so that means in all these 4 examples, they are all fully parentheses. So now it's useful if we review the rules of matrix multiplication a little bit, because we did that before, but now let's look at it more closely, because it's critical, very important to understand the rules before we look at the problem of how to chain up the matrix multiplications. So if we zoom in to only 2 matrices, okay, we know that the 2 matrices A and B can be multiplied only if they are compatible. Okay, so not all matrices can be multiplied together. They must satisfy that the number of columns in the first one in A must be must equal the number of rows in the second one, in the second matrix B. Okay, say if A is a P by Q matrix which has P columns and the P rows and the Q columns, and then B must be Q by R matrix. So the number of rows of B must equal the number of columns in A. So only by that way we can multiply A and B together. And the resulting matrix C, the product of A times B, C is a P by R matrix. So the P comes from the row numbers of A, and the R comes from the column numbers in B. Okay, so it's like we put P times Q and the Q times R together, and then we can eliminate the Q in the middle, and what's left is just P and R. Okay, I think that's a quite straightforward rule to follow. Okay, so now we just consider a very naive triple for loop implementation of doing this matrix multiplication. Okay, we're not doing any fancy optimization like Strassen's algorithms, because here our point is not about making the product between two matrices fast, but we are really caring about how to organize the way to how to select the best way of parenthesizing matrices so that we can have the minimal amount of computation needed. Okay, so let's just look at the pseudocode for this triple for loop implementation of multiplying two matrices together. Okay, so we have A and B as inputs, so we first check if the columns equal the rows, and then we define, so we use some intermediate variable P and Q and R to remember the number of rows and columns in the two matrices. Okay, so the result will be stored in the new matrix in C. Okay, so we know that it must be a P by R matrix, so we allocate that many space, and there's a for loop. Okay, the first layer of for loop is the loop that iterates over the number of rows in matrix A. So iterates over from 1 to P. Okay, so iterates over all rows. And then there's a second for loop that iterates over the columns of A from 1 to R. Okay, the columns of B, which is from 1 to R. Okay, and and this column from 1 to R is also the column in C, right? Because C has R columns as well, which is the same as B. Okay, so for each element in C indicated by C with subscript ij, that means it's the elements of the ith row and the jth column in the resulting matrix C. So we don't know it first, so we let it to be 0. And how do we get the new elements in position I and j? Is doing some accumulative summation which we will compute using a third for loop. Okay, so in this third for loop, it iterates over the number of columns in matrix A, and it is also the number of rows in matrix B, because they all have the same number. They all have Q columns in A and Q rows in B. Okay, so taking that ith row of A and the jth column in B, yes, and then we compute for each element in that row and the vector, in the row and the column, we compute the dot product, right? So that's the so here line 9, AIK is the ith row and the kth column elements in A, and bkj is the k's row and j's column. Okay, so within the body of this second j for loop, I and j, they never change, right? We only change q, or we only change k for k from 1 to q. Okay, so it's like a cumulative dot products of that sum up all the products between the elements in A and B. Okay, so that's how we compute the Cij. Okay, so if we plot the two matrices together in a graph, so A should be like this blue square. It has P rows and Q columns, and the matrix B has Q columns and the R rows, so the Q matches here. Okay, so and the resulting will be P by R C matrix. Okay, so the number of the efficiency, so how fast this algorithm runs depends on how many scalar multiplications are done here, right? So we are doing multiplication here. So because it's a triple for loop, right? And the first for loop ranges from 1 to P, and the second for loop ranges 1 to R, and the third for loop ranges from 1 to Q. So there P times Q times R, that many scalar multiplications need to be done, right? So by scalar multiplication, I mean the multiplication between two numbers, okay, like aik times bkj. So there are that many multiplications needed in order to compute the whole C, matrix C. Okay, that's that's the results from this nature of the triple for loops. Okay, so that is very useful information. This P times Q times R. This is very useful information, because whenever you are given two matrices, okay, and I'm telling you that the first one is P by Q, A is P by Q, and the B is Q by R. So you can immediately tell that, okay, the cost of computing A times B is P times Q times R. Okay, and done. That's it. That's the cost we need in order to compute A and B, A times B. Okay, and totally defined. These P, Q, R are totally defined by the sizes of the input matrices. Okay, so that's rule for multiplying two matrices together. And now let's see how this critical information PQR are gonna influence how we compute the chain of matrices. Okay. Okay, so now we know that the computational cost for multiplying two matrices together is PQR in terms of the number of scalar multiplications. So how does this gonna affect, or how does this information gonna inform us about the problem of matrix chain multiplication? So now let's start from looking at how different ways of parenthesizing the chains or the sequences of matrices will affect the running time. So let's consider a short chain which just consists of three matrices, A1, A2, and A3. And also we assume that they are compatible. Okay, so if you look at A1, its dimension is 10 by 100, 10 rows and 100 columns, and A2 is 100 by 5, 100 rows and 5 columns, and for A3 it's 5 rows by 50 columns. So as you can see, 100 equals 100 here, and the 5 here matches the 5 of A3, so they are compatible. It is valid to write a product like A1, A2, and A3. Okay, so let's just first consider the one way of doing the parenthesizing. So let's just first multiply A1 and A2 together, and then use their result to multiply with A3. So in this case, how many scalar multiplications need to be done? So according to our previous slide, we just need to consider the quantity of P times Q times R. So to A1 times A2, the P times Q times R is 10 times 100 times 5, which is 5,000. Okay? And the resulting matrix is a 10 by 5 matrix. Okay, that's our first step. And then our second step is to multiply the resulting matrix, the 10 by 5 matrix, with A3, right? So in this computation, the P times Q times R is 10 times 5 times 50, which is 2050. And then we are done. Okay, so in total, we have 5,000 plus 2,500 total scalar multiplications needed if we are doing parentheses like this one. Okay, so of course there are other ways of doing the parentheses, and now let's just examine a second way. Okay, so what about we do the A2 times A3 first? Okay, and this time the PQR is 100 times 5 times 50, which is 25,000, right? Which is already much greater than the total number of the first way. Okay, so here is just the step 1. Okay, and the resulting matrix is 100 by 50. Okay, in our step 2, we need to multiply this 100 by 50 matrix with A1, in which the PQR is 10 times 100 times 50, which is even more, 50K. Okay? Adding up these two steps together, we have 75,000 in total scalar multiplications if we choose to multiply A2 and A3 together. Okay? So you see, we are doing the same computation, right? The results of the first way, A1 times A2 and then times A3, is totally equals the result of A1 times parentheses A2, A3. But the total number of computation of scalar multiplications, they differ a lot. Okay, so that's why we say in the case of we have a chain of matrices, it's really important to choose the correct or choose the optimal way to add parentheses, so that the number of scalar multiplications needed will be much improved. Like in this case, we have a 10 times improvements if we choose the proper way. Okay, so that's why we need to consider this as a necessary problem to find out a optimal solution. So now let's define this matrix chain problem more generally. Okay, so let's assume that the chain we have has n matrices from A1 to AN and we also know the dimension for each matrix in it. Like, for example, for the matrix AI, the I's matrix, we know that it has a dimension in P subscript I minus 1 times or by PI. Okay, so the P subscript I minus 1 is the number of rows of AI, and the P subscript I is the number of columns for AI. So the problem is to parentheses the products A1 times A2 times A until AN in such a way that the number of scalar multiplications is minimized or optimized. Okay? So that is a general definition of the problem. So now, before we thinking about an efficient solution to it, we can always start from some naive or brute force way. Okay, so in terms of just in order to solve this problem without considering the relevant cost, we can think of just several brute force ways. Like we can check all possible parenthesizations. So in theory, that is possible. Okay, given a sequence, we can always enumerate all possible ways of doing the parenthesization. Okay? So in this case, how much roughly running time will this brute force way will cost us? So we can start by thinking about this question. Okay. So given a chain of matrices like this, so let's first consider the the final layer, the last layer of parentheses, right? So eventually, the chain of multiplication becomes the multiplication between two matrices, right? And where these two matrices come from are not considered here. So now we don't consider the previous steps. So we just consider the last step. We're just considering the last step, how many possible ways of parentheses are there in the last step. Okay, so if the inputs matrix chain has 10, say we have 10 matrices, and obviously the last layer of parenthesization has 9 possible options, right? We can either insert the parentheses here between A1 and A2, or between A2 and A3, or between A3 and A4. Okay. So we can simply let P of n to be the number of possible parenthesizations for a chain of n matrices. Okay, we define some function. Okay, and then we can use a recursive way to denote the total number of parenthesization, right? So in the case of these 10 input matrices, we know that P10 must be the summation of P1 times P9 plus P2 times P8 plus until P1 times P9. Okay, so because P of 9 is the number of possible parenthesizations by multiplying A2 to A10, right? And P of 2 is the number of parenthesizations between A1 and A2. And the P of 8 is the number of parenthesization between A3 and A10. Okay? So that's a very recursive way of doing this computation. Okay, so given this recursive way of definition, we can write the recurrence equation or recurrence in such a way. Okay, so when the input is n, and if there's only one matrix in it, then it must be 1. Okay, and if it's greater than 2, then the problem becomes the summation of a bunch of products in the form of pk times p of n minus k. Okay, because we are splitting the chain into 2 parts. The first part has k elements, k matrices, and the second part has n minus k matrices. Okay, so if we try to solve it, we will find that this equation has a very dramatically big boundary. Okay, it basically has a larger, it grows faster than the exponential function. Okay, it is a super inefficient way if we want to enumerate all possible ways of doing parenthesization. Okay, so therefore we need to consider a more efficient solution using a dynamic programming approach. Okay, so one of the conditions of applying a dynamic programming approach to a problem is that the problem should demonstrate some optimal substructure property. Okay, that is to say, we we can construct, we can solve we can get an optimal solution by combining or by solving, by having the optimal solutions to the subproblems. Okay, so now let's look at whether we can do this composition. Actually, we already kind of showed some hints of doing so in the previous slides. Okay, so now we need to use some notations, okay, to help us doing the problem structure, optimal substructure analysis. So we use this this notation, capital A with subscripts I to J with two dots in between I and J. Okay, so to indicate to denote the resulting matrix from the product, from the chain products, from AI times AI plus 1 until A subscript J, in which case A must be smaller than J. Okay, so we're using this shorter, basically this shorter notation to denote the long chain product from AI to AJ. Okay, and in order to parenthesize the products, we must split the chain between some points. Okay, between some points indicated by this integer k. Okay, we must choose some k that's between I and j. Okay, and that is a point where we split the chain. Okay, in that case, we are actually splitting the chain between the matrix, the k's matrix AK, and the k plus 1's matrix AK plus 1. Okay, so there are always some k that we should choose in order to do the split. Okay, so when the k is chosen, we can write the chain products from AI to AJ on the left of this equation to the combination of two parts on the right. Within the first parenthesis, it's the chain product from AI to AK. And on the right, within the right parenthesis, it's the chain product between k plus 1 to AJ. Okay? And if we use the shorter notation here, we can rewrite the right part, the long sequences, the long chains into a more compact form. Like we use A subscripts I to K to indicate the results of doing the chain product within the left parenthesis, and then you use the A subscript K plus 1 to J to indicate the result of the right chain product. Okay, so now if we write this way, the A subscript I to K and A subscript K plus 1 to J, they represent two matrices actually, right? So this one is a matrix and this one is also a matrix. They are just the results of multiplying a chain, two chains respectively. Okay, so now the total cost. So now let's consider the total costs of in terms of scalar multiplications, of doing matrix multiplications. Okay, so the total cost of doing this chain is the summation of the cost of computing a subscript I to K plus the cost of computing A subscripts from K plus 1 to J and the additional cost of multiplying these resulting two matrices together. All right, so that makes sense, right? Because the total cost is doing the left half, and this cost of computing A subscript I towards K is what is required to compute the left subchain. Okay, and this part is the cost required by computing the right subchain. and this additional multiplied cost is the result. It is the cost for multiplying these two matrices. Okay, so according to just recall the in a few slides ago we introduced the cost of multiplying two matrices together, right? Remember the quantity of P times Q times R as the total number of scalar multiplications needed in order to multiply two matrices. So that rule applies here as well, okay? Because we know that the resulting matrix A subscript I to K, its dimension must be P subscript I minus 1 times pk, or P subscript I minus 1 rows and the P subscript k columns, and the right resulting matrix must be P subscript k by P subscript j. Okay, so that's determined, that's the nature of the matrix. That's just following the rules of matrix multiplication. Okay, so if we want to multiply these two matrices together, the cost of the scalar multiplications is Pi minus 1 times Pk, see the Pk matches here, and times Pj. So now we can, given these rules, we can rewrite the cost of the total cost of obtaining the chain multiplication results. Okay, so we can state the optimal substructure like this. Okay, so suppose that in order to optimally parenthesize the sequence, the chain from AI to AJ, we need to split the product between AK and AK plus 1. And within these optimal solutions, these subchains from AI to AK, and the second subchain from AK plus 1 to AJ, they also must be optimally parenthesized. So, okay, so these two subchains are the subproblems that we need to solve. Okay, so we can split the original problem into two subproblems. We must first optimally parenthesize the first subproblem and the second problem, and then we combine them together. Okay, so we need to consider all possible values of k in the search for the optimal k. Right? There are a lot of possible k's, okay, a lot of possible positions to do the split. So we want to search for the optimal k. So another way of framing this problem, we can use this more mathematical or simplified notation. Okay, so let's assume that we have some magical function or magical procedure called dp, and this is a function that knows the optimal, that tells us the optimal solution. Okay, for any sequence. So let's just have that imagination in our mind. Okay, so if we call that dp function on our input, say from a1 to a5, it will return the minimal. It will return the results in terms of the minimal number of scalar multiplications. Okay, so in order to get the solution, it must be the choosing the minimal among such combinations. So the first one is to split the input chain into A1 as one single chain, and the second chain is A2 to A5. And then we call the dp, the magical imaginary function, onto these two subchains respectively. Right? So dp of A1 will tell us the optimal cost or the minimized cost of chaining A1, and dp on this A2 to A5 will tell us the optimal solutions of chaining A2 to A5. And the additional costs comes with the final step when you multiply the resulting two matrices together. Okay, so this P0 and P1 is just the dimensions of A1, right? And this P1 and P5, they are the dimensions of the resulting matrix of A2 to A5. Okay, so this is just one possible way of doing a split. Okay, and there's also a second way, which is to chain A1 to A2 together and to chain A3 to A5 together. And the additional cost is a bit different because now the resulting matrix is in the dimension of P0 by P2 and P2 by P5. Okay, and that is the cost of multiplying the two resulting matrices together. And the third way is to chain A1 to A3 and A4 to A5. And the last way is to chain A1 to A4 and A5 as a single matrix alone. And the additional costs there are different. Okay, so we all just to the global solution, the final solution to this original problem must be the minimum among these four, right? And again, let's look into these subproblems. The dp on this subchain from A2 to A5, it also has an optimal substructure, right? Because this is a different problem, but in the same nature, right? We're just calling dp on the different sequence. So in order to solve this one particular subproblem, we also must choose among a bunch of minimum values, must choose the minimum among a bunch of solutions. Okay, so we could possibly decompose the chain from A2 to A5 into A2 and A3 to A5, right? And there comes additional cost of combining, of multiplying the two resulting matrices. Or we can split by A2, A3, and A4, A5, or A2, A3, A4, A5, right? All comes with additional cost. Okay, so this solution must be chosen among these three possible candidates. Okay, and the same rules apply to all the instances here. So in order to solve dp on A3 to A5, we also must choose among the minimum among these two cases. Okay, so now is the key points. So in order to solve all these subproblems, we already see that there are a whole lot of overlaps, right? So in order to solve this subproblem in red color, we must solve dp from A3 to A5, this smaller subproblem, right? In order to solve the red one, we must solve this blue one. Okay, but later on, when the red one is already solved, when we try to solve the A3, A4, A5, we are solving it again, right? The blue part indicates that the same subproblems, they are solved twice. And again here, dp A4 to A5 is also solved, but here it's solved again. See, so there are overlaps of the subproblems. The same subproblems got repeatedly solved again and again. Okay, so that is a bad thing if we want to implement a recursive algorithm based on the optimal substructure. But it's a good thing that it's telling us that we can use dynamic programming to remember to the results of some subproblems after we solve it for the first time, and then we just store it. And when the next time we come across to the same problem again, we can just retrieve it from the lookup table, from the array, or whatever you use to store it, without solving it again. Okay, so this overlap between subproblems is another indicator that we can solve the problems with dynamic programming. Okay, so which is a lot of overlapping substructures. Okay, and this is quite similar to it's a very typical structure to the rod cutting problems and or the Fibonacci problems we have come across before. So now, based on the imaginary magical function called dp, which can be called upon a sequence or a chain of matrices, we can further use some tricks to rewrite all the notations to have a simpler representation of the problem. Okay, it's just a way of reframing the problem. Okay, so now instead of calling dp function, write it upon on top of a chain of matrices from AI to AJ, because we know that this chain from AI to AJ starts with the index I and ends with the index J. So that's why we can write it in a simpler, even more simpler way by calling it dp with I and J to indicate where the chain starts and where it ends, right? So that's the totally equivalent way. Okay, so using this simpler notification, I'm going to rewrite all the equations that I have shown here. I'm going to rewrite all the optimal substructure here into an even more simpler form, much simpler form. So say eventually we want to know dp on 1 and 5, which means from A1 to A5, the chain. Okay, so this solution must be from dp11 plus dp25 plus the cost, additional cost, or dp12 to dp35, dp13 dp45, or dp14 dp55. Okay, so that's the same thing, total equivalence notation to the previous slide. Okay, so it's just so this dp of ij is just the intermediate representation to makes it more abstract, to make the representation of the subproblems more abstract. So given the fact that we can simplify to this extent, so why bother we use dp? Why bother we use a function on the two arguments I and j? Why not we just use a more straightforward data structure? Okay, we can simply represent the dp function on I and j with an element in a 2D array, right? Think of I and j as the indices, as the row index and the column index in the 2D array. And let's give it a name m. We just use one letter instead of two letter dp, right? So why not just we use a elements in the 2D array to indicate the solution of having the optimal parenthesization on the matrix, on the subchain of matrix chains. Okay, so if we replace dp on ij with mij with brackets, with square brackets like the elements, now we can simply further rewrite all the equations here. So the final solution becomes m15. Okay, it is the minimum among these four. M11, which is originally dp11, and m25, which is originally dp25, and this thing never change. They come along with the additional cost of multiplying two resulting matrices. Okay, and then we just replace everything into m. Okay, so that gives us the advantage of a very quick way to save the solutions into a data structure, right? Because we're using dynamic programming, we want to, after we solve some subproblems, we want to save that problem into the corresponding position in the data structure. Okay, so M15 is a final solution. It is the elements of the first row and the fifth column in the 2D array. And the subproblem of dp on 1,1 is the elements saved in the first row and the first column elements, and so on. Okay. So now, if we put these 4 equations together and give it a minimal function here, we are writing the same thing into this more compact form. Okay. So the final solution of M15 equals the minimum amount such choose the k such that the combination is minimized, right? It must be range from 1 to k and plus the m of k plus 1 to 5 and the additional costs, right? K ranges from 1 and must be smaller than 5. Okay? So this is the very compact way of showing the optimal substructure of the problem. Okay? Or more generally, if we replace the numbers 1 and 5 with I and j, we can do the same thing, right? So now k must range from I and b to j and be strictly smaller than j, and the additional cost is in the form of pi times pk times pj. Okay. So now we are pretty close to the parts of how dynamic programming will be implemented, but given this general form of optimal substructure, we can easily implement some recursive but not non-dynamic programming approaches. Like we can easily write some recursive algorithms. Okay, so in this recursive implementation, we can say let's the ith row and j's elements mij to be the minimum number of scalar multiplications needed to compute the chain from ai to j. Okay, so that's the meaning of the elements in that 2D array. Okay, so when I equals j, so there's no matrix at all, so their value should be 0. Okay, when I equals j, they should be 0. So in other cases, mij should be written in this form, which is exactly the form that we shown in the previous slides. Okay, so the recurrence is kind of like this way, right? So we write a recurrence in this way. When I equals j, mij should be 0, and then when I is smaller than j, then we will choose the minimum among these solutions. Okay, so if we do implement a recursive algorithm, we can find that this algorithm runs in exponential time, which is as bad as the brute force way. And the brute force is to simply enumerate all possible ways of doing the parenthesization. And actually, this one is essentially doing the same thing, right? If we implement the recursive algorithm on it, but without memorizing the solutions. So the reason behind it is that the subproblems are solved repeatedly, I guess, which we already shown in 2 slides ago. Okay, so all the notations that we have laid out here, they will help us to implement some very efficient dynamic programming-based solutions to the problem of matrix chain multiplication. Okay, so we will start introducing some bottom-up dynamic programming solution from the in the next video lecture. And that's it for the lecture today.